If two variables, x and y, are correlated so that they have a linear relationship, we may want to use one to predict the other. Recall the beginning of the term when we drew scatter plots. The x-axis is the explanatory variable, the y-axis is the response. When the relationship has a linear pattern, we can fit a line to it. That will allow us to predict values of y given values of x. You can draw a line between any 2 points. Hopefully you remember the equation for a line, which is y equals mx plus b. If you have 2 points, you can find m with y2 minus y1 divided by x2 minus x1, then plug in one of the points to find b. For these 2 points, 1, 1 and 6, 7, the slope is 1.2 and the y-intercept, the b, is negative 0.2. The equation for the line running through the 2 points is y equals 1.2x minus 0.2. We're usually going to be dealing with many points, and they're not all going to be on a line. How would we fit a line in this case? Here we have 3 points, and you can't draw a single line between all 3. The number of possible lines we could draw is infinite. Here are a few possibilities. Because there are so many options, we need some criterion that will tell us which is best. There are different ways you could go about it, but the most common is least sum of squares regression. If x, y is one of the points from your data, and x, y hat is the point on the line with the same x coordinate, then we use the difference, y minus y hat, to measure the distance from the point to the line. If we add up these differences for every point, that gives us a measure of how far the line is from the points. We square the differences to keep them positive. Sometimes they will be negative, sometimes positive. If we add negative to positive, we lose information. That's why we're squaring here. There's also a form of regression where you use the sum of the absolute values of the differences, but the math is easier if you use sum of squares. Y is the point in the data. Y hat is the point predicted by the line. The quantity y minus y hat is called a residual. We want to find the line that has the smallest sum of squared residuals. This is the original line passing through 2 of the points. The distance from the line to each of these points is 0. This difference squared is 2.56. The sum of squared residuals for this line is 2.56. This is another line I drew. Its equation is 1.5x minus 1. These are the y hat values. The sum of squared residuals is 3.5. This is higher than the last line, so this doesn't fit as well according to the least sum of squares criterion. For the green line, the sum of squared residuals is 1.68. I got this line from R. The equation is 1.1579x plus 0.4737. It can be shown that when you fit these lines, only one will have the smallest sum of squared residuals. You can find the m and b using calculus, but it's very tedious, so R will do it for us. I believe that linear regression was discovered in the early 1800s, but it wasn't used much until the 1950s or so, when computers came along to do the calculations. This is the syntax you use in R. If you have two variables, x the explanatory, y the response, LMY squiggle x gives you this output here, the intercept and the slope. The idea is that y is this linear function of x, but there's some error attached to each point, so that the data doesn't all fit on a single line. This error could be measurement error or just some kind of variation in the process that prevents x and y from having a perfect linear relationship. For now, we'll assume that this error is normally distributed with mean 0 and standard deviation sigma. It's actually not that important for it to be normal, but we really want this sigma to be the same for every error term. As always, Greek letters represent parameters. Beta 0 and beta 1 are unknown parameters that we're trying to estimate with the least squares line. B0 and B1 are the coefficients we get from fitting the line. In the last example, I had B0 equals 0.4737 and B1 equals 1.1579. The regression equation tells you the mean value of y for a given x. We also refer to this as the expected value given x. It's the value we predict for y given some value of x. The y-intercept is the value when x equals 0. When that happens, we have y hat equals b0. It's the value of the response variable when the explanatory variable is 0. B1 is the slope. An increase of 1 unit in x leads to an increase of B1 in y. And if B1 is negative, there will be a decrease in y. If I have y hat equals B0 plus B1x, and I add 1 to x, I get I'll make this a star. Increasing x by 1 increases y hat by B1. Here's an example from the Open Intro package. 16 volunteers were randomly assigned a number of beers to drink, and afterward their blood alcohol content was measured. Let's fit a least squares regression line to this. I go into R and enter this lm command. The syntax is always y squiggle x. Y is the response, which is BAC here. X is the explanatory variable. The number of beers explains the BAC. The output from R gives me the slope and y-intercept for the line. The line is y hat equals negative 0.0127 plus 0.01796x, and it's drawn to the right. To interpret it, we can write it like this. In regression, the hat means predicted or fitted. A person's predicted BAC is negative 0.0127 plus 0.01796 times the number of beers they drink. If a person drinks 0 beers, their predicted blood alcohol content is negative 0.0127. It doesn't make any sense to have negative BAC, but that's typical. Sometimes these intercepts have a meaning, other times not. It's just giving us the best fit to the data. For each beer a person consumes, their blood alcohol content is predicted to increase by 0.01796. A person who drinks 6 beers is predicted to have a blood alcohol content of 0.09506. There was a person in the experiment who drank 6 beers, and their BAC was 0.1. The residual for the observation is y minus y hat, observed minus predicted, and that is 0.00494.